Good afternoon. My name is Christian Luke. I'm an engineer in the Austin Energy Green Building Evaluation Development Group, and welcome to our November 2025 seminar, Green Tech Horizons. This is our bi-monthly seminar series highlighting topics important to sustainability in the built environment. Before we dive into that information, we'll start with a few announcements of local events and put direct links in the chat now. Our AEGB e-learning platform offers on-demand courses so you can earn continuing education credits at your convenience. We upload recorded webinars and other virtual learning resources like tours, workshops, and case studies. Log in to register and see what's new. The Austin Green Awards are next week. Join us for an evening honoring Austin's exemplary green buildings, landscapes, and infrastructure. Celebrate the recipients of innovative, forward-facing design strategies that respond to rapidly evolving environmental, social, and health imperatives. Get more details on their website. Join USGBC Central Texas on November 20th for a Green Buildings walking tour in the heart of downtown Austin. Discover how our city is leading the way in sustainable design, resilient infrastructure, and energy-efficient construction through programs like LEED and Austin Energy Green Building. Visit their website for more details and check out their other upcoming events. AIA Austin is hosting their annual holiday event on December 10th at Distribution Hall. Check out their website for more details soon. This seminar is being submitted for AIA Learning Units, GBCI CE Hours for LEED, and AICP for those who attend for the entire webinar. All certificates will be emailed. A follow-up email will be sent with links to the recording and other resources. It will take a little bit of extra time for video editing on this seminar. We will be adding this to our e-learning platform as well. Next, we have our AA quality assurance slide. And then these are today's learning objectives. If you have any questions during our speaker's presentation, please be sure to use the Q&A window throughout the seminar. We've scheduled time at the end of our seminar to discuss them, but for any of those we don't get to, we'll get those answered after the presentation and sent with a follow-up email. Today's topic is Green Tech Horizons. Our speakers will show how sustainable building innovations are shaping the future of high-performance design. They will highlight breakthrough technologies that make buildings cleaner, smarter, and more resilient. We'll hear how these advances are transforming the way we design and operate buildings for a healthier and more sustainable future. Our first speaker today is David McKenna of Cushing, Terrell. David McKenna is a PE and Lean Grade Associate. He is a mechanical and plumbing designer for Cushing Terrell based in Central Texas. An expert in balancing the art and science of mechanical design, David helps his clients build for the future with thoughtful, sustainable, and efficient systems. His experience includes small business construction, hospitals, schools, mission-critical facilities, and military bases. He has a deep understanding of every phase of the construction process and provides services in energy modeling, controls engineering, and construction administration. Please welcome David.
Good afternoon, and thank you for that introduction. Appreciate that, and huge thank you to Austin Energy Green Building for hosting us and giving us a platform and an opportunity to kind of talk through some of these things that we see on a daily basis. So with that, we'll jump right in. I'm going to start a timer. So can y'all see that? I'm going to go ahead and share my screen. Y'all let me know when you can see that.
Looks good.
Excellent. All right, let's dive right in. So I'm a mechanical engineer, and there's a huge onus on mechanical engineers currently to drive down a building's energy consumption, and that's primarily because HVAC and building controls tend to be one of the largest contributing components to a building's energy usage. Depending on the building type, it can contribute up to 40% just by itself of a building's energy usage. So again, massive onus on us as designers to sort of pick sustainable design solutions, and that may not be the cheapest, but might be more cost effective in the long run, and ultimately save energy over the lifespan of the equipment. And so what I'm going to do here is highlight sort of some of the strategies that we use as design engineers to make that happen. As a practicing engineer, we kind of see two types of buildings, without getting into the various vertical markets. I'm not going to talk necessarily about specifically hospitals and data centers and those sorts of things. I'm just going to talk about high level. The two main types of projects that we see are new builds and then retrofits. And there are opportunities to employ some of these technologies in both. So we'll go ahead and start with new builds, because those actually tend to be easier. So what we're looking at here is, I'll let you all read that list, but ultimately, when we're looking at a new build or a greenfield construction site, ultimately that process starts with a discussion with the owner, and that's a great opportunity for us to kind of coach those owners and developers on what it means to select efficient equipment right from day one. And so oftentimes that means a higher upfront cost, but again, frequently what owners want to understand is what's that payback period, and what is the value proposition there. And so when we're looking at brand new buildings, we can right off the rip select variable speed pumping systems, variable speed fans, variable speed compressors, mag bearing compressors, those sorts of things in our equipment that we specify to try to reduce the building's energy usage, essentially. And so there, with a new building, you kind of have free reign, and we can pick some pretty creative design solutions there, be it chilled beams or radiant heating, those sorts of things, decoupling outside air from the building mechanical systems. And there are all sorts of really cool strategies that we can employ. But again, it all starts with a discussion right up front with the owner to try to help them to understand why it is that we're going with this direction. The other type that we typically see are retrofits, and this gets a little bit trickier because you're often sort of stuck with the systems that you have to some degree, and you might be looking at a 40, 50, 60-year-old building that might have constant volume chill water systems, or constant volume air, or even constant volume compressors and refrigerant-based systems and things like that. So there's some low-hanging fruit for us as design engineers to kind of retrofit variable speed pumps and fans and things like that into those, and that's typically where we would start. Part of that, and we'll talk about this a little bit more in a second, is providing the building with sensors so that we can actually control those devices appropriately. And so a large part of that relies on A, the sensors, but B, the sensors being installed and calibrated correctly. And you start to, when that starts to happen, the system literally gets smarter and enables us to sort of trim, respond, and optimize that component's energy usage. So again, some examples here on how we can sort of accomplish that. And we'll talk a little bit more about that here as we progress. One of the main topics I'm going to be talking about is ASHRAE Guideline 36. This affects both types of buildings that we just talked about. There is ASHRAE 90.1, which is sort of the design minimum standard, which we design to as engineers and architects. But ASHRAE Guideline 36 sort of goes above and beyond. And so every year we're kind of seeing the energy code push us in that direction year after year. And so as design engineers, this is sort of becoming the new standard to which a lot of engineers and firms are designing to. And we'll see why in these next couple slides. So ASHRAE Guideline 36 is really a treasure trove of information for us. it enables us as design engineers to kind of go in there and in some instances, it's not always this easy, but we can, in some instances, copy and paste a lot of these control strategies and sequences directly onto our drawings. So what we do obviously is specify the equipment, and then it's really important to convey how we expect that equipment to run. And so that's what an increasing part of our job as engineers is becoming, is really getting involved in the control systems and the controls infrastructure side of things. And so ASHRAE Guideline 36 really helps us understand how best to optimize that equipment's operation. And in many instances, we can see an energy efficiency savings of up, 20, sometimes even up to 30%. And there are a few case studies out there that are already available online. If y'all want more information on that, I can link it. So again, part of this comes down to having a smarter building and having those sensors installed, be it in the ductwork system or the chill water system or the hydronic heating system or whatever it might be. And so what I'm going to talk about next is sort of what that looks like from a software standpoint, and then what that looks like from a hardware standpoint, and how we marry those two together to ultimately see energy efficiency savings. And hopefully that paints a pretty clear picture on why this is now becoming the new standard. So what we're looking at here are some examples of the software side of things. These are some of these sequences, for instance, fault detection and diagnostics. These are things that are primarily and ventilation efficiency. A lot of these are going to be driven by the back end or the software of your building management system or BMS. And so, with this, we can look at, for instance, ventilation efficiency. If our carbon dioxide, instead of providing a constant volume of outside air, like it would have historically been done, we can actually measure CO2 within the space. So that requires a CO2 sensor, the hardware within the space, and then obviously the software to interpret that. And so what we can do, again, this is just one example, is we can actually reduce the amount of outside air if we see that carbon dioxide level dropping. Basically, the less people in the building, we don't need to supply quite as much outside air. And in warm, humid climates like Central Texas, that can be a huge energy savings, because dehumidifying outside air is enormously energy intensive. A couple other examples here. Discharge air temperature reset is another good one. Historically, a lot of HVAC systems have provided just 55-degree air at a constant volume, and then you let the thermostat tell you to turn it off. What ASHRAE Guideline 36 is proposing is they really harp on the trim and respond logic. So we actually do the opposite. Now what we're doing is we're cutting down we're setting up that discharge air temperature as high as we possibly can to save energy, until one of those zones basically cries uncle and says, oh, it's too hot, so we actually need to reset it further down. And so again, these are, on the software side, some of the strategies that we can look at to incorporate into our mechanical design to try to help take advantage of some of these energy savings and optimization. So again, that's sort of the software side. What we're going to look at next is the hardware side. So I'm going to show you two examples. One is a control schematic of an air side economizer, and hopefully this helps paint a picture as to why we do some of what we do. So as I mentioned earlier, increasingly large part of what we do as mechanical design engineers is basically providing the control strategies and controls schematic diagrams to communicate to the controls contractor and ultimately tell them how we envision this building to run. So each of these circles here that hopefully y'all can see indicates a controls point for this piece of equipment. This is one air handler with, I don't know how many, a lot of points. I didn't count them, but you can quickly see how this building could have thousands of points if you have multiple air handlers all serving that space. So each one of these is associated with either an analog output or an analog input or a digital input, digital output to the BMS or building management system. And this schematic, I think, really helps to show how we can save energy. So in this case, again, we're looking at an airside economizer. With this sort of setup, we can look at things like outside air temperature, and the control sequence might read something like, okay, well, when the enthalpy of the outside air is lower than the enthalpy of the return air, as indicated by this temperature sensor, then we can close this damper. the return air damper, and basically flush nothing but clean outside air through your building because it's free cold air. So in that case, you won't have to run your chill water coil, which means that you can turn your compressor off back at your chiller, which is the main energy hog of the system. So it's basically free cooling, and it's essentially a mechanical equivalent to opening a window instead of running your AC. So again, enormous energy savings there that I think, when you marry the software and the hardware side, you can see hopefully quite clearly how this serves to save energy. So again, one example of this is the air side economizer. The other one that we'll look at briefly is the water side economizer, which is a very similar system. What we're looking at here is a chill water plant schematic of a controls diagram. So in this particular case, we have 2 water-cooled chillers, 2 cooling towers, primary pumps, secondary pumps, condenser water pumps. So it's pretty typical setup for what we see. And then sometimes what we'll also see depending on your climate zone, we may see a water side economizer, which is essentially a fluid to fluid heat exchanger that lets you bypass your chillers. And so you don't need to run the compressor. So when the outside air temperatures and water temperatures are optimal, we don't need to be producing cold water because the water coming back from the cooling towers is actually cool enough to provide what we need to the building. And so again, when we have all these sensors within the system that are able to monitor those conditions and control those conditions, we can use those to our benefit and ultimately save building energy. So these are some of the items that we're seeing reflected in the energy code year after year. We're seeing more and more air side economizers or water side economizers in Central Texas, but also in other climate zones. So again, I just wanted to highlight, these are 2 sort of, I think, low-hanging fruit examples that kind of show you, what it is that we're doing here with the software and the hardware, and ultimately the impact that it has on our mechanical system. So there's a tremendous opportunity for us to drastically reduce HVAC system operation. But with that, the goal here as mechanical designers, again, ASHRAE 90.1 is really our new minimum for energy efficiency, and we're aiming really higher with ASHRAE guideline 36, and we'll see more and more of that as we get here into the future. So at the end of the day, it does require a little bit of upfront investment to get your building to the point where it has those sensors and we can actually get them under control. But it is a discussion definitely worth having. So with that, I will go ahead and hand it back to you, Ricky. I want to be respectful of everybody else's time. So thank you all.
Thank you, David. Christian?
All right, thank you. Our next speaker will be a recorded presentation from Massimilano Santi. Massimilano is the Managing and Sustainability Director of World Energy Absorption Chillers in Europe. Massimilano is a sustainable cooling expert with nearly 30 years of experience in the absorption cooling and heating sector. He is a graduate in international studies for sustainability. He has dedicated his career to advancing energy efficiency, decarbonization, and the circular economy solutions for air conditioning and industrial cooling. His expertise lies in promoting the use of natural refrigerant absorption chillers and heat pumps powered by waste heat. This waste heat is often recovered from industrial processes like power plants, district heating networks, or from renewable resources such as solar or geothermal. A passionate advocate for climate-friendly technologies, Massimilano strongly supports the adoption of refrigerants with low or zero global warming potential and no PFAS, as well as the integration of chillers with natural-based solutions for sustainable cooling in commercial buildings. Throughout his career, he has held roles in business development and training, overseeing the implementation of absorption technology across a wide range of applications on 4 continents. Today, he serves as Managing and Sustainability Director at World Energy Europe, the European Office of World Energy, a Korean manufacturer of lithium bromide absorption chillers and heat pumps. And with that, we'll begin Massimiliano's presentation.
Hello, everyone. My name is Massimiliano Santini. and I'm the Managing and Sustainability Director of World Energy Absorption Chillers Europe. First of all, let me thank Austin Energy for inviting me to speak today. It's a great pleasure to contribute to this important discussion on sustainable building technologies. I'd also like to apologize for not being able to join live, but I'm very glad to share this recorded presentation, and I truly appreciate your time and interest in learning more about how we can decarbonize building cooling through low power natural refrigerant absorption chillers. A few words about us. World Energy is a South Korean company founded in 2004. We manufacture absorption chillers and heat pumps only. We have supplied chillers worldwide, both standard and customized units for numerous applications, to mention a few, industrial, marine, commercial, oil and gas, among others. And our product range starts from 30 to 2,000 refrigeration tons. So what exactly is an absorption chiller? Unlike traditional chillers that use electric compressors, absorption chillers use heat energy, such as hot water, steam, or hot gases to drive the cooling cycle. They use the most natural refrigerant, water, and have no moving parts, no vibration, very low power consumption, and work under vacuum condition. So the absorption chiller chemicals, in addition to water as refrigerant, we use lithium bromide as absorbent solution. We have a GWP of 0 and the ODP of 0. The chemicals are non-toxic, non-flammable. The refrigerant is not an HFO. The refrigerant contains no PFAS, and most importantly, there is no risk of refrigerant phase out due to legislation. Here we can see the main difference between a traditional vapor compression cycle and an absorption cycle. The main difference is in the way we transport the refrigerant vapor from the evaporator to the condenser. As you know, in every chiller, the cooling effect is achieved by transferring the heat from the chill water to the liquid refrigerant. This heat transfer cools the chill water and heats the liquid refrigerant, creating a change of state from liquid to vapor. Then the refrigerant vapor has to be taken to the condenser to return to the liquid state and restart the cooling effect. To do that, compression chillers use a compressor using electricity to do this work, while the absorption cycle, as you can see, has two additional heat exchangers, the absorber and the generator. So after the refrigerant vapor evaporates in the evaporator, this is absorbed by a solution of 60% lithium bromide, which is a salt, so is hygroscopic and at certain concentration can absorb water vapor. After absorbing the refrigerant, the solution gets diluted from 60% lithium bromide to 55%. The diluted solution from the absorber is then pumped to another heat exchanger, the generator, where it finds the heat source. Thanks to the high temperature of the heat source, the refrigerant vapor is separated from the diluted solution, and thanks to this separation, the refrigerant vapor can reach the condenser and return to the liquid state. At the same time, after the refrigerant separation, the solution gets concentrated again back to 60% to restart the absorption process. Here you can see the what happens inside the evaporator. So in the evaporator tube, we have the chill water, so the water that must be cooled. You have here the refrigerant droplets falling down on the tubes, and when they touch the tubes, the heat of the chilled water is transferred to the refrigerant, and this transfer makes the refrigerant droplets evaporate. By evaporating, we extract latent heat from the chilled water and we cool it, like in this example, from 54 degrees to 44 degrees. This happens thanks to the low evaporation temperature, because at the pressure of 0.29 inches of mercury, the evaporation temperature of water is just 42.8 degrees. Then you can see here on the right side the concentrated lithium bromide solution droplets absorbing the refrigerant vapor. The total heat to be dissipated from the absorption chiller is the sum of the cooling capacity, so the evaporator thermal power, and the thermal power of the heat source. The heat is dissipated using the cooling water that circulates in both the absorber and the condenser heat exchanger. The efficiency of an absorption chiller, expressed as the coefficient of performance, COP, is the ratio between the cooling capacity, so the evaporator thermal power, and the thermal power of the heat source, so the thermal power of the generator heat exchanger. There are two types of absorption chillers, single stage and double stage. Single stage chillers work with low temperature heat sources, while double stage chillers need a much higher temperature to work. The difference is also in the efficiency. The COP of single stage units is lower than 1 and greater than 1 for double stage units. The minimum temperature of the chill water that can be achieved is 32 degrees for standard units. For special brine chillers, we can cool the brine down to 19.4 degrees. Absorption chillers can work in partial cooling loads with a turn-down ratio of 20%. The efficiency at partial load is quite constant, and the cooling demand can be modulated using a control valve for the heat source, unlike compressor that use a variable speed drive inverter. As you can see here, the efficiency of the chiller varies based on the heat source temperature or heat source pressure in case of steam. So, for example, with 284 degrees hot water, the efficiency can be as high as 0.85, and with hot gases or 1200 degrees hot gases or 116 degrees psi steam pressure, the efficiency can be as high as 1.5. This slide illustrates the most typical heat sources for absorption chillers. Cogeneration with heat recovered from engines, turbines, and fuel cells. Industrial waste heat, such as furnaces, flue gases, or post-combustors. District heating networks, very used, especially in commercial or institutional buildings, or renewable heat with solar, thermal, geothermal, or bio-waste combustion. As it can be seen in this chart, the cooling accounts for more than 1 gigaton of CO2 emissions per year globally, mostly due to electricity consumption for chillers and air conditioners. As global temperatures rise, electricity demand for cooling will increase sharply. The cooling degrees days are also rising, so we must take measures to decrease the electricity consumption for cooling, as well as the reduction of CO2 emissions related to that. So absorption chillers offer a contribution to sustainability and circular economy, because we use waste heat and negligible power consumption. We ensure the climate mitigation by achieving significant CO2 emissions reduction. And so we support the global climate action, especially the goal 13 of the UN 2030 Agenda for Sustainable Development. Let's see here in this table a comparison between double stage and single stage absorption chillers versus water cooled and air cooled compression chillers. So in this table, we can see the electricity saving that a building owner having a heat source can obtain by implementing absorption chillers. So a 300 tons water-cooled compression chiller has a power consumption of approximately 182 kilowatt. 333 kilowatt is the power consumption of an air-cooled chiller, while absorption chiller, considering also the extra power needed for cooling towers compared to compression chillers, absorption chillers have a total power consumption of 34.5 for the double stage one and 39.5 for the single stage one. It means that compared to the compression chiller, we have a very high power consumption saving between 142 kilowatt and 300, almost 300 kilowatt of power savings. So approximately a range in percentage between 78% and 89% of electricity saving. Considering only 3,000 hours of operation at full cooling capacity, and considering a carbon dioxide emissions factor in pounds for pounds of CO2 equivalent for each kilowatt hour of saved electricity, we can obtain CO2 emissions reductions between 346,000 and 725,000 pounds of CO2 equivalent per year. Let me show you some of our installations. This is 517 tons chiller powered by 193 degrees hot water from a cogeneration power plant for a university in Washington, D.C. These units are installed at a museum and library in California, and are powered by 635 degrees exhaust gases coming from gas turbines with an efficiency of 1.49. This is an installation for a total cooling capacity of over 8,000 tons for a mall, resort, and casino complex in South Korea using 203 degrees hot water from district heating. We have also installations in airports. Here we have a total cooling capacity of 7,900 tons. These chillers are fed by 203 degrees hot water from a district heating network. Industries have a lot of waste heat. This is a petrochemical application Louisiana in the USA, and where we installed a total cooling capacity of over 2,700 tons using very low temperature, 149 degrees hot water from waste heat. Passengers ships have also waste heat. This case is 568 tons absorption chillers powered by 194 degrees hot water recovered from marine propulsion engines. Renewable heat can be also used. This is an installation where the absorption chiller is powered by 194 degrees hot water from rooftop solar thermal collectors for a military base in Africa. Thank you for your attention. I hope the brief overview I shared about absorption chillers has been helpful in providing ideas for their implementation in green building contexts. If you would like more information or have any questions, please feel free to contact me at the email address below.
So that was Massimilano, Santini, and now over to Christian.
Thank you, Ricky. Again, if you have any questions for Massimiliano, please put them in the Q&A chat. We'll pass this along to him and have him respond to those in the next few days. All right. Up next, our third speaker today is Michael Ziebell of Lute and Ether. Michael has a PhD in biophysics from Stony Brook University and has pursued a career in biotechnology research in Boston. In response to the urgent need for solutions in clean technology, Michael has applied his scientific knowledge to building companies that offer climate-aware technologies. This includes green water technologies that focus on optimizing green algae to produce high-value chemicals, Cambridge Transport Labs, a company developing solutions to drive efficiency in transportation, and most recently Lute and Ether, a consultancy created to drive adoption of carbon-free energy solutions. Michael lives in the suburbs of Boston, a hub for clean technology startups. Please welcome Michael.
Hi, everyone. Thanks for this opportunity. Many thanks to Austin Energy for this. Let me share my screen if I can. One of the organizers yell out if you can't see anything or if you can't hear anything. I am part of Lute and Ether, a project development company. It's a startup. We just this year were part of the Cleantech Open Accelerator, which is a national program to help small businesses get a footprint in the clean tech space. As a product developer, what we're interested in doing is identify opportunities and exploit them for the benefit of communities. What I'm going to talk about today is a focus on carbon neutral energy, namely hydrogen. Unlike, for example, some of the other docs from Massimiliano and David, this is more theoretical about what to look for in the years to come. I don't expect you to jump out of your seat right now and buy a fuel cell. But what I hope happens is that you sort of put hydrogen in the back of your mind as something that could be a really great solution for organizations and for cities overall. Now, a lot of the conversation you'll see has a bit of a transportation flavor to it. And the reason for that is that it really is helpful to sort of think about how it compares to fossil fuels. I'll talk about some of the sources of hydrogen. And here we're thinking about clean or almost clean. Green is the best, and then there's blue and other flavors, including white. And electrolysis, geologic hydrogen, and then very quickly spent oil wells is sort of interesting. I won't spend a lot of time talking about that. Then very key, I'd love to explore the cost of all of this, because I think now in the current era, we're thinking about what is that need for adoption? And I think how much is it going to cost is the fundamental question. And then look at opportunities where hydrogen might play a role. And I think the key message here is not all solutions are suitable for hydrogen, and a couple of use cases at the end. I'll just quickly stop here. Audio and video, okay. Ricky, you're okay with this? I'll take that as a yes.
Sounds good to me.
Perfect. Great. So electrolysis is perhaps the most interesting to explore theoretically. And this might hark back to your days in middle school science fair, where either you or your competitor next to you shooting for the gold #1 star, grabbed a 9-volt battery, attached electrodes to the positive and negative, popped them into some alkaline water, and watched hydrogen and oxygen evolve at the anode and cathode. And that's the principle of it. And I guess that's the beauty of it, that it's really that simple. And the evolution of hydrogen then can be routed towards energy. So on the left-hand side is a polymer electrolyzed membrane, and that's essentially the version of that, where instead of having just an alkaline solution, you have water entering on the anode side, pushed by pressure, and combines with a catalytic layer. And as the hydrogen evolves across the membrane, it then, under the electrical source, then separates into hydrogen and oxygen. And the oxygen then evolves on the anode side, and water and hydrogen then evolves on the cathode side. The water is separated from the hydrogen. The hydrogen is pressurized and can be used for energy. The image on the left-hand side is sort of the parallel comparison to that, which is using that same sort of technology, except to evolve electricity. So hydrogen is pumped in on the anode. It interacts with a catalytic layer and crosses a membrane, and the protons are separated from the electrons. Electrons pass through an external load. That's your electrical source. And the protons then interact with oxygen to reduce it and form water. It's this combination that's being proposed here, and the use of fuel cells is explored for buildings as well as for transportation. So that's electrolysis in a nutshell. The rub is how much electricity it really takes. This comes out of some collaborations I've had with Brian Deberine. He's head of the Colorado Hydrogen Network up there in Boulder and Denver. And he went to the trouble of working out the math. How much electricity is really required to produce it? Let's call it a kilogram of hydrogen, whatever that means. And clearly the vast majority comes in the electrolysis, but then there's some other ancillary activities, including the compression, storage, and what's not listed here is the transportation. That all adds up to some rather profound number. And he estimates around 56 kilowatt hours per kilogram of hydrogen. And it's worth mentioning, though, that if just as you sort of think through this, so what does this mean? What is a kilogram of hydrogen? Loosely speaking, a kilogram corresponds to about a gallon of gas in terms of energy equivalence. But considering a fuel cell, let's take a vehicle, for example, just a passenger vehicle. There's around a 2.5 efficiency factor. So really, any way you look at it, you're taking around between 20 and 30 kilowatt hours to drive a vehicle equivalent of 1 gallon of gas. And so then I'll leave it to you to work out in your mind how much that corresponds to the cost when you think of the electrical costs in your area. Now, the beautiful thing, of course, would be is if the source of electricity comes from solar and wind, and then you have a perfect system that's truly green. But I think we all know I'm speaking to an audience which I'm sure appreciates the fact that the electrical grid is so integrated, it's kind of hard to carve off to just the renewable energy part. But that is indeed one thing people talk about. I'll just leave it there for that. The other interesting area that is being explored is this idea of what's underground. The U.S. Geological Survey came up with this rather profound map. I think it's a few years old now, maybe 2022, 2023, where the blue regions are supposed to indicate geological formations that may, and there's a real qualifier there, have hydrogen stored in them. And when the USGS produced this, it stimulated a flurry of activity, including investment in organizations and companies that might be willing to explore this. I mean, can you imagine popping down a well in Michigan and coming out with just a steady flow of hydrogen? There's a company called Coloma, which I think is leading the way in this. There's a few others as well. Forgive me if there's individuals in the audience that are saying, wait a second, what about the other company I know about? The question is whether this is really going to be instituted at a commercial level. The interesting thing about this is that people who enter into the drilling for hydrogen space are often former oil and gas or current oil and gas engineers, and that speaks to the need to have really qualified individuals who think about these problems in a profound way. The difference is that when you pop in a well in the Gulf of Mexico and you get 500,000 gallons a day of crude, that's unlikely to be the case for hydrogen. It's going to be a niche space here and there. But nonetheless, it's exciting. And the reason it's exciting is that it could be very cost effective relative to electrolysis. I'll just very briefly mention there's another interesting set of technology that are looking to capture hydrogen from other sources. For example, here, this is from spent oil wells, where either using a chemical or biological process can stimulate the production of hydrogen for use down the road. And you might say this is a niche opportunity, but putting it all together, this could be really interesting way to gather some energy. So now, very quickly, let's just quick look at the pricing. And again, this is for transportation, but I hope for those of you who are thinking more at a sort of civic level, just consider this as a way of seeing, well, when would it be that that the cost of hydrogen per kilogram makes sense? Now, in the upper table, the message on this third row down, target price per gallon, my apologies, is supposed to indicate what is possible given the efficiencies in the price per gas. So, for a regular passenger vehicle, if you can sell a kilogram of hydrogen for $8.75, you're breaking even for passenger vehicles. That's not the case, for example, if you believe this type of analysis for heavy trucking on highways, where it's just it's not possible. So you have to sell for much less than that. So one quick anecdote here. To my understanding, the price of hydrogen in California presently is hovering around $30 a gallon. So that speaks to the need to really think clearly about whether the price is going to be possible for adoption, which is a key part of the pillar. I'll show you that later. So then the table down below, very quickly, is a way of if you consider geologic hydrogen to be a real thing, and it's there's some big questions there, it starts looking like the price could be similar to SMR, and if that's the case, it could be half the price of electrolysis. That's not to say that electrolysis doesn't have a role, but it might be more of a niche opportunity if geologic takes off, and there's some real hope for that. So now down to the matter of where hydrogen as a fuel could serve a role. And I think the message in this table is it isn't a great fit for certain areas. For example, just popping on hydrogen to produce electricity in the electrical grid just may not really make a lot of sense. However, when you think about this massive upscale of data centers and their need for a steady flow of electricity for stability and so that their systems maintain sort of a degree of regularity, hydrogen is considered a really good backup system and also compares favorably to lithium batteries. Transportation, yes, for certain niches. That's the point. Maybe not for heavy long distance trucking, but perhaps for transportation. One interesting, I'll just rush down to the bottom here, combined heat and power. That could be a great play where hydrogen fits into some of the other strategies. And indeed, this is related to, for example, what Massimilano and David were talking about, where it fits nicely in. Maritime, this is for shipping. The question here is whether there's a play there, but there's a mandate. There's the international shipping organizations are saying, dudes, you need to clean up your act. You need to stop burning that heavy oil that you see coming out of the smokestacks and ships. So something has to be done, and hydrogen is being explored. Whether it's possible or not is another question. Okay, very quickly, the point here is when we think about now putting my project development hat on, where does it fit? Certainly technical cost, but acceptance is a huge one, and that has to do with what we're seeing potentially in California as a bottleneck. It's available. You can load up your car with you can pump hydrogen into your car, but there's just not a lot of uptake yet. Room for hope. This just came out last week. Again, California seems to want to lead the way in this. I guess maybe there's a real mandate. There's a need. I think California has always been interested in thinking about cutting edge technologies, but it also is incredibly costly, and I hope they're doing the right thing. But one of the generation facilities in Los Angeles will convert to hydrogen from natural gas by 2030. The fact that it had to happen because the natural gas turbines were actually from the 1950s. They have some images on there. So they had to be converted to something. Why not hydrogen? So that's exciting. Then in real time, there's communities across the United States that are looking at hydrogen as a source for public transportation. And that's I would say, a good fit. But these buses are around 2.5 times the price of CNG powered buses. So, you really have to have the willingness and the money to do so. So another interesting project that's coming out of Europe is the idea of blending natural gas and hydrogen. And, you might say, well, what's the point? Why do you even need to go to this trouble? One of the messages is that it is a way of drawing down the reliance on CNG. So if you're in a country that has some pressures, that's important. And the other important part is that it can use the existing pipelines. So that's an example of where hydrogen, while it's not a profound replacement, potentially can fit into existing infrastructure, which is particularly exciting. And then another potential examination is, again, this combined heat and power. And in this case, the model is using multiple sources of energy to power an infrastructure. This is sort of a strategic. It's not in real place, but hydrogen would serve in this case as an energy storage facility, similar to the methane that's stored over here in the gas storage there. So that's another good way that hydrogen might fit in the near term. That's the key. This can happen in short term. There is an organization in Ann Arbor looking at this controversial topic of decentralized energy. And again, it may not make a lot of sense for those of you in the audience who are saying there is no such thing as decentralized energy in the United States, but it's worth examining that case, especially in constraints that are likely to happen. People I talk to talk about real problems, making sure that we have steady electrical supply in the years to come, in part because of higher demand. I mean, data centers are mentioned, but it's not just data centers. So in this situation, it would be a collection of some 50, 100 residential units gathering together and having either an independent set of energy sources or backup systems that can manage brownouts. And in that situation, hydrogen might play a role as part of the backup system there. And I think that is the end of what I want to talk about. There's a couple of sources here which I'm happy to share with you. And thank you for, I think the conclusions though are really, let's make sure that when we present new technologies to the world, we're being very mindful of what the adoption looks like. And I think most people are going to say, tell me what it's going to cost before I take it on. And then stay tuned, because I think the story does change as the technology improves. So with that, I thank you for your attention.
All right, thank you, Michael. Our final speaker this afternoon is Dragan Djurdjanovic from the University of Texas at Austin. Dragan obtained his bachelor's in mechanical engineering and bachelor's in applied mathematics in 1997 from the University of Nice in Serbia. His MS in mechanical engineering from the Nanyang Technical University in Singapore in 1999, along with his master's in electrical engineering and PhD in mechanical engineering in 2002 from the University of Michigan in Ann Arbor. Dr. Djurdjanovic explores methodologies for transforming data into useful information and further into operational decisions with applications in advanced semiconductor manufacturing, automotive engine systems, biomedical research, and HVAC systems. He served as the Associate Director for the National Science Foundation Engineering Research Center on nanomanufacturing systems for mobile computing and mobile energy technologies from 2018 to 2023. Dr. Djurdjanovic has co-authored more than 150 archival journal and conference publications. He serves as an associate editor in the IEEE Transactions on Semiconductor Manufacturing. He is a fellow of the International Society of Engineering Asset Management and an associate member of the International Academy for Production Research. Please welcome Dr. Djurdjanovic.
Thank you very much for this introduction. I wish to thank Austin Energy for the invitation to present our work today. So I am going to share my screen. Can you please confirm to me that you see my screen?
Yeah, looks good to me.
Okay, wonderful. And I'm trying to move away this. Anyway, I'll start my presentation. So, no, I don't want to leave. I wanted to. I apologize. So I'll be talking to you about data analytics for efficient control of HVAC systems. From this long introduction, I hope you have understood that I'm a very mathy person, that I like to use big data to achieve, a better control and better usage of our physical systems. So amongst applications of my work are actually HVAC systems, heating, ventilation, and air conditioning systems. So I'll briefly introduce you with the concept of physical analytics, which is a methodological paradigm that I utilize in all of my work. Then I'll talk about the dual mode model predictive control, DMMPC method, which I think is a very interesting and highly enabling control method, which can be employed in various places, and we have especially been playing with it in the domain of HVAC systems. So I'll then show to you our work in applying the DMMPC to controlling of HVAC systems, leading to some interesting observations in the sense that that advanced control led to us being able to obtain significant energy savings utilizing the same equipment, i.e. without investing into any new equipment. Just by more cleverly controlling our system, we can actually make significant energy savings. So the source of my work is really this data deluge that we see in modern physical systems. So data that's emitted by physical Internet of Things is already larger than the data generated by social and computer networks, with double the growth rate actually than what we observe in physical systems. And most of my work actually still is in semiconductor manufacturing. And as one observes, and maybe you're hearing in the news how much that is actually exploding, I believe that within 5 years, physical Internet of Things will be a place where biggest achievements and biggest breakthroughs in data analytics will be happening, not anymore in the realm of social and computer networks like Google, Apple, Facebook, and those kinds of places. This data deluge really gives us a great opportunity to better control quality of operation of our systems, to better optimize trajectories which our systems need to follow, and then control the way our systems actually operate. Even further, this data deluge enables us to actually utilize the concept of transfer learning and actually take lessons that we learn while making certain products, or take lessons in certain domains and apply them to actually controlling and optimizing applications in other domains. Like if we learn how to make these toys using additive manufacturing, maybe then we can utilize those lessons in optimizing and quickly controlling the process of making a golf club or gearboxes. So data analytics I see as a process where we are transforming raw data into useful information, and then into decisions how to operate our systems. Information is a loaded word, and so when it comes to information, we can actually utilize data to model the system and detect departures away from nominal behavior. That means the classical modeling, fault detection, diagnostics. Then we can actually utilize data and advanced machine learning to actually do control of our system. That means to make our system do what we want it to do, regardless of external disturbances, noise, and inaccuracies. Finally, we can utilize our data to actually optimize what we want our system to do, thus enabling better control of our system utilizing our data. So in undergrad education, I just literally walked out of the class a few seconds ago. Okay, not a few minutes ago. We teach our students to utilize classical methods of control theory, classical methods of modeling and monitoring, classical methods of operations and industrial engineering, which are founded in first principle physics and formalisms of classical mathematics. On the other hand, our friends in Facebook, Apple, Google are able to do these transformations of large amounts of data into useful information and decisions, utilizing effectively statistics and optimization, just lifted to a much higher degree, scaled up dramatically because of computational capabilities that we have. We call that machine learning and artificial intelligence. However, these methodologies that are very well advanced I don't probably need to tell you that classical first order physics, first principle physics, and classical tractable mathematics based on linear ordinary differential equations don't work very well with complex systems such as HVAC systems or nano-manufacturing. But also I can tell you that our friends in Google, Apple, Facebook are very good at recognizing, facial pictures. They're able to recognize what your preferences in terms of marketing are. Basically, for them, we're all sequences of vectors. They know what website you're on, how long you stayed there, what was the next website you went on, how long you stayed there, what did you do there, or who did you speak to, where were you when you spoke to that person, who did you speak next, and so on and so forth. So for them, we're all sequences of vectors, which means that they live in the world called discrete mathematics. Our systems, HVAC systems, live in the continuous world. They're described by partial differential equations, non-linear, very complicated. So we need to actually build the bridge between discrete mathematics and continuous mathematics. And ways to build those bridges are different. One way is to use physically inspired, data curation and signal processing, and then couple that with discrete mathematics. So for example, you can extract interesting features out of airflows, out of current flows in the motors that you use for in the pumps, and so on and so forth, and then use machine learning on that to achieve, let's say, fault detection diagnostics. Or we can use first principle models like we used in our HVAC system. They are very good first principle models of HVAC systems, and then simplify them utilizing maybe reduced order models like neural network models, and then based on that achieve fault detection, diagnostics, and control if possible. And that's the realm that's referred to in this wonderful talk by Dr. Hendrik Hamann from IBM Watson Research Center as the realm of physical data analytics. His talk, which you can find at the link over there, refers to is actually titled "When Big Data Gets Physical," which really is describing what are the challenges we have in the physical world, where you know our sensors are emitting a lot of data, our actuators are emitting a lot of data. We had one of the earlier talks about one of the earlier presentations talk about variable speed pumps, adding more sensors to the HVAC system, and in that realm you get way more data than you can deal with, and really it's an interesting problem. How do you utilize physics to digest that data and couple it with actual advanced mathematics, machine learning, and AI? So my talk will focus on controlling of HVAC systems, and it's extremely important to control them. And I will start by talking about the need for thermal management of data centers. You're probably hearing in the news every day how much energy is consumed by data centers today. Then high standard manufacturing environment like semiconductor fabs, where you need to maintain temperature and humidity at a perfect level to produce 2 nanometer features across 300 millimeters of a wafer. That's 8 orders of magnitude that you need to bridge, and controlling humidity and temperatures is extremely important. Research labs with precise air conditioning and demands here at UT, we got lots of those. Then large volume stadiums and arenas are very interesting problems because of high air flows, and just in the case of high volumes, you have extreme non-linearities and extreme uncertainties in parameters of the system that you're trying to control, and traditional approaches based on PID control or on-off control, bang-bang control just don't work well, and actually suboptimality becomes bigger and bigger with larger volumes and larger non-linearities, basically. So this is a little somewhat stale story, which I actually derived from the Academy for Production Research, of which I am a member, which shows just in manufacturing we have 14% of actual energy is being actually utilized in manufacturing. 14% is expended on air conditioning. So in manufacturing realm, this is very important, and really our study that I'm showing to you today was motivated by that. So I'm a manufacturing researcher, and I thought maybe it's important to try to apply some advanced mathematics to HVAC control in manufacturing systems. But I believe that the achievements that I will show to you are applicable in other places, and I'll talk about that at the end of my talk. So traditional HVAC systems are relying on relatively basic control methodologies, on-off control, PID control, which really doesn't require a lot of computation. It is effectively trying, because the task is usually relatively simple. You're trying to keep constant temperature, and just anytime you deviate from that temperature, you switch on the flow or switch off the flow. PID control, a little bit switching on-off is smoothed. So I will just give you an example of my colleague who actually works in a company that builds data centers. In one of the earliest examples of data centers, that was about maybe 5-6 years ago, they were called by a customer who was complaining about the vents shutting down and opening up, because the control mechanism was basically on-off control, where they would open the vents when they needed to cool the data center, close them when the temperature was actually cooled off. It was actually Pacific Northwest where this was happening. Now, what they actually had an issue with was that the vents would open because the data center was too hot. The vents would open, but it was raining outside, so the raindrops would fall on the vents and cool them off instantly. And they said, oh, I need to shut down. They would shut down. Then instantly they would again be super hot. They would open up. Then rain falls on, shut down. So the data center was ruining itself and it was just, you would think that with an investment that's in billions of dollars, you would invest a little bit more into your control system and understand, and do it in a little bit more advanced way. So That being said, I want to talk about this methodology, which is a variation of model predictive control. Model predictive control is a methodology that many of you likely have heard, where we are utilizing a good description, utilizing data that we are collecting, history of system states, history of our control inputs, and maybe add on top of it a model of the system. And with HVAC systems, we have models of the system, of the room we are controlling, we're cooling, as well as models of our HVAC equipment as well. And then knowing what we wish to achieve in terms of, let's say, desired temperatures in the room, we can optimize our control signals up to a certain horizon to make sure that the predicted outputs converge to where we wish to be. The methodology often requires advanced optimization, which, if we have a large system with lots of sensing and lots of actuation, that means lots of variable speed pumps and lots of temperature sensors across, let's say, sports arena, becomes a very difficult problem, which requires you to solve something called sequential quadratic programs at scale. But today, with machine learning, we can do that. We have computational power to do that, especially if you're talking about data centers, if you're talking about sports arenas. We definitely have ability to install such computational capabilities. On top of this, what my students and I have done about 6 years ago was actually find a way to ease the computational burden by finding a boundary around desired trajectory of, let's say, temperatures and flows, within which you can switch on the linear controller. So that means we can characterize this boundary around the desired trajectory. Once you enter that boundary, you actually can switch on to a simple linear controller based on the state feedback, and that controller will have proven provable stability and performance. Its performance actually dramatically is better than the classical PID control. So let me show to you an example where we applied. So we're utilizing a model that's publicly available of a relatively large volume, about 300 cubic meters volume. So, you know, a largish room, where we were controlling 9 controllable inputs and actually controlling, utilizing multiple air vents and airflow. So I really liked one of the talks earlier, which talked about David McKenna's talk, where he was talking about adding sensors and adding variable speed pumps to our system. Once we add such equipment, you can really control better and track better the desired temperatures. So just to illustrate to you, the tracking performance was really fantastic. The PID control is the red line, and the DMMPC is actually totally under the blue line, because under the black line, under the reference line, because the deviations are very, very small. What is nice about this, the only problem with the DMMPC, the PID gets lost and then finally finds the trajectory. Then when you get into this change, you can see again they separate a little bit, but because PID reacts to errors. There has to be some error before it actually works on the control. Whereas model predictive control knows the trajectory and predicts what you should be doing before actually bad things happen to you. So what was very interesting is obviously the tracking performance was much better utilizing our model predictive control. Actually, here's the tracking error of temperatures. It's so tiny that it's hard to visualize it. But one thing that my student and I were really kind of surprised with was that we noticed the chiller was utilized in a much more efficient way, that the vents were actually strategically opened and closed because we knew what transition we were trying to achieve with our model predictive control. And so the energy consumption became very, very much better than we were achieving with PID or smooth PID, which is like a little bit better implementation of PID, where we look at the past trajectory and use simple exponential smoothing to predict where the next points should be. So this was a very interesting result. Good, better tracking with significantly reduced energy, 8.5% reduction. Then we said, hey, what if we add noise to this simulation? So we added a multiplicative noise, and we noticed that the more noise we add, the energy savings became better, and trajectory tracking was actually still robustly better than what we were achieving with PID control. So adding noise, when we added noise to this model, advanced control enabled us to actually increase our energy savings while maintaining trajectory tracking. In addition, we actually were pretending like, okay, what if a fault happens? What if our fan motor, changed? So resistance increased by 20% in the fan motor at some point. And you can see that our model predictive control adapts to these situations, and energy savings are even bigger with our model predictive control still being able to deliver desired performance. So what is the main message that I want to give to you? Advanced math utilizing model predictive control can give you superior tracking performance with energy savings. This is beautiful. What is really important is that this kind of methodology is naturally made for MIMO systems. When you have many actuation capabilities like variable speed pumps and many vents that you need to control, and you don't control them on off, but you can partially open and partially close them. Stability is proven. You're not going to have that unstable situation where it closes, opens, where basically it's destroying itself, like it was that data center was doing in Washington State. And then, more interestingly enough, is we can track any trajectory we want. We can actually, rather than going for temperature transition, we can actually smooth those transitions. So what was very interesting was that we can optimize the trajectory that we wish to execute while we are going with temperatures from temperature 1 to temperature 2, and formally drive those two temperatures in zone 1 and zone 2 to desired levels with increased savings. So you can see that different trajectories are leading to different energy consumptions. So message that I wish to give is, utilize these advanced control techniques, especially given that you're adding so much exciting equipment into HVAC systems, especially when you're doing it with large volumes like airport, sports arenas, where nonlinearities and flows are bigger, and therefore PID controllers are less and less, or linear controllers are less and less efficient. And then finally, in data centers and in, let's say, airport buildings where you have periods of low occupancy and periods of high occupancy, you can also track weather outside. You can actually predict and optimize these trajectories that you wish to track with your HVAC systems. And through such optimizations, you can actually achieve energy savings. So, long story short, energy savings can be achieved through new equipment concepts, new physical concepts, but they can also be achieved through advanced data analytics utilizing the existing equipment. And that's where I will stop.
I'd like to thank all of our panelists. If each of you could come back on camera now, we'll go ahead and start our Q&A section. If anyone has questions they'd like to ask of our panelists and hasn't yet put them in the Q&A chat of WebEx, please do so now, and we'll do our best to get to all of the audience questions. All right. Our first one this afternoon is for David. The question is, do you have any experience designing systems for buildings that have been designed to passive house standards, or if you could kind of elaborate on how the choice of systems and controls varies based on the quality of the envelope or the tightness of the particular design?
Yes, to answer your question, yes, I do have some experience with that. Ultimately, that your choice of system is in many instances driven by your envelope design. For instance, if you have fenestrations or things like that are opening and closing, that may impact your choice of HVAC system. Certain systems may only be able to effectively cool or maintain a space depending on whether or not it's refrigerant based or chilled water based. They each have different properties and things like that. So hopefully that answers your question.
I have one more for you. Do the advanced control sequences in ASHRAE Standard 36 require a higher level of HVAC commissioning?
Good question. Yes, I mean it is going to require a commissioning agent to not only be familiar, obviously, with ASHRAE Guideline 36, but also know how to implement those. And then additionally, it's also a time investment, right? You know, we're going above and beyond here over ASHRAE 90.1, and so it's going to require a little bit more time, more sensors, and ultimately a deeper understanding of control system to be able to implement it properly.
Thank you. Our next one is for Dr. Djurdjanovic. Could you explain more about the type of data from the example used about the turbine engine?
So yeah, this was a classical HVAC model that's built, as you have seen, in the I think late 90s. I left a reference to that. So the data is classical data that you would find in regular systems. So that means the duct openings and closing, the position of all the ducts, the air flows in the ducts, and temperature readings inside the two zones that were being cooled. How those data was used, they were actually coupled with high fidelity models. So that means there were PDEs that described humidity and temperature inside each of the rooms. So humidity measurements and temperature was also available and were controlled. So that was maybe the only unusual thing, was there was humidity available, humidity measurement. Everything else was standard vent openings, temperatures, and flows. And the physical model was used to combine them all together.
I have another question for you. How can these control sequences you discussed be used to help reduce building energy consumption during a particular window of grid constraint? Like in the evenings between 7 and 10 p.m., the grid has its highest carbon intensity and price. So what can be done to shift that load kind of forward or backwards?
Yeah, good question. It really, the only way I would see it is you can schedule temperatures more efficiently based on the prices that you know, so that the targets to which you wish to transition are optimized based on that cost. The work that I was showing to you today was, once you decide where you wish the targets to be and when, that transition from where you are to where you wish to be should be done in a very clever way, in an optimized way, not like, okay, I'm here, get me there now. But actually, if you can smooth that transition, energy can be saved through that transition. So the work that I'm showing was more in realizing that transition in the best way. I think one can add cost parameters so that not only are you optimizing the transition, but you're also optimizing the targets to which you're going. We have not done that, but I think that can also be accomplished.
All right, thank you. My next one is for Michael. Can you discuss when you think hydrogen will reach parity with our existing fossil fuel sources, or if that's even likely?
Fair point. I would make the case that the technology for electrolysis is likely going to level out. It'll get a little cheaper for electrolysis, but some of these other sources, for example, geologic hydrogen, have to play a role. And then potentially, yes, there could be an opportunity. Now, of course, what we're not factoring in is the cost of the carbon. And if you factor that in, that does change the equation a little bit. But in this era, we're not talking too much about that until it becomes clear how we're going to manage carbon credits globally.
Thank you. And then I'm going to turn it over to Ricky now. I believe he has a few more questions for our panelists.
Can you hear me?
Yes, now.
Yeah.
Okay. Sorry about the gap there. I wanted to give our panelists also an opportunity to ask questions from our panelists, because I've been on panels where I had questions from other panelists and never got around to asking them. But I take the privilege of being here, so I want to ask two questions. The first one is to Dr. Dragan. When you talk about a central utility plant, which is going to be serving thermal energy storage function for a large campus-wide use, and if you wanted to look at heat cascades to be retrofit over there, do you feel that this algorithm approach that you have could be made optimized to the each individual retrofit to the heat cascades that are put? We have a central utility plant coming up at the Austin airport. I do foresee that at some point in the future, we may be adding heat cascades there. So this is the question, how granular can this go?
Yeah, good question. These are all questions that are very practical. In my opinion, the best way is always to actually have an integral approach where you will actually model also the interactions between the heat cascades. However, I think maybe a good first cut would be to control them separately, and that way see how much benefits you're getting. But long story short, again, I'm seeing everything as a differential equation, and the two zone system that I was showing on the slides had about 20 states in the model that included, like I said, vent openings, closings, and air flows. It is not difficult to actually have state space systems that have 200 states, and that would actually include an integral model of cascading heat stages. So I cannot give you a definitive answer. I would probably need to see more detailed models and compare to what we have done in our work. But usually integral models are better performing. Fragmented models are easier to implement, and you can more easily quantify benefits and understand if things don't go well, why they didn't go well. So maybe usually strategic way to solve things is to go fragmented way and then model the integrated way.
Yeah, thank you. My next question is for Michael. When you look at you gave examples of data centers as a source of large energy requirements. The other area that we have in the Austin area is a growth for warehousing, for example, and warehousing has a tremendous amount of energy needs, which are including forklifts and other equipment which go in there. Do you have anything that you think is in the green tech horizon for us to consider for that?
That's a fair point. In fact, hydrogen-powered forklifts are a thing. And to my understanding, Amazon and some of the other huge warehousing organizations do currently use hydrogen forklifts. So it's a really good point. And I think the challenge is to build on that tradition and see how green hydrogen might fit into that model. To my understanding, Amazon gets a delivery of hydrogen that's using SMR. I mean, it's a great start. And as somebody recently said to me, don't let the perfect get in the way of the good. Let's start somewhere and get hydrogen in place. So yeah, to answer your question, Ricky, warehousing is a really good place for the use of hydrogen, specifically for forklifts.
All right. Well, we are just about at 1:30 this afternoon. So I'd like to thank our panelists and all of our attendees for joining us today. Please take a moment to complete the survey link placed in the chat. Your feedback is greatly appreciated and it helps us plan for future webinars. As a reminder, everyone registered today will receive a follow-up email with resource links and a webinar recording. Today's webinar attendees will receive a continuing education certificate for self-reporting GBCI continuing education hours and AICP CM credits. If you provided us with your AIA number during registration, we will report your AIA learning units for attending this webinar. If you couldn't attend the entire webinar or want to share this information with colleagues, this seminar will also be included on our new e-learning platform in about 6 weeks, where you can watch the recording and take a quiz and earn CEU credits. Check out our current courses at the link in the chat and log in to get started. Thank you again all for attending. This concludes today's webinar.
Thank you.
Thanks, everyone.
Thank you for joining us. Have a good day. Bye.
See ya.